Hello everyone, this is Dr. Hopkins, narrating the next video in our series. We are continuing with one of my favorite subjects, and that's kinetics. We learned about rate laws last time. Now we're going to learn our first method for determining the rate law. That's the method of initial rate. So let's start out. What is a rate law? Kind of a reminder. If we had a reaction, a general reaction, A plus B getting products, then we would write the rate is equal to some rate constant, which we'd have to empirically determine, the concentration of A raised to whatever order that is, and the concentration of B raised to whatever order that is. So N and M are orders. So a rate law, as we said before, is empirically derived. So we'd have to do it by experiment. We can't just say, oh yeah, look at that. I know that one is first order and that one's second order. We have to actually measure it. And there are two ways to do that. The first way is the method of initial rates. That's the subject of this video. And the second one is the integrated rate law, and that's what we'll do next time. We'll use both of those as two different ways to determine the rate law of a reaction. And then if we know the rate law, we know if we change the concentration, we can change how fast the reaction will run. All right, so the method of initial rates is basically what we're going to do is we're going to measure the reaction rate at the very beginning. Okay, at the very beginning, when we've mixed our reactants in, we can actually control the concentration. Once the reaction's gone a little ways, the concentration of the reactants have changed enough that we really don't know what they are anymore. So at the very beginning, we know, hey, if I put 0.1 molar in at the beginning, it's 0.1 molar at least for the very start of the reaction. And so what we do is we set up, and I've just got a general one reactant reaction. You would set up a trial where you would run it with 0.1 molar A and measure how fast it runs. And then you might set up a trial where it would run with 0.2 molar and see how fast that runs. And then we can compare the two rates. So if the rate doubles from the second trial to the first trial, that means the reaction order is first in A. If it quadruples, it's second order. And of course, we know the order doesn't have to be integral. It can be non-integral. So we just can do the math to determine, since we've doubled the concentration, we should know the concentration-dependent rate from that. So let's do an example. And typically, the method of initial rates, you end up with these kind of tabulated data. Now, what you do if you go in the lab is you control these initial concentrations. So we have three experiments. We have F2 and ClO2. We have our reaction. Now, remember, the stoichiometry doesn't matter in terms of the rate law. All right, so I've moved the table to the notes app because I didn't have enough room in my PowerPoint slide to do all of the kind of math that I want to show you. So we've got our table of F2, ClO2. These are our concentrations and our rates. The rate law is going to be the rate is equal to some rate constant, F2 to the X. X is our order of F2, and ClO2 is the order of Y. So what we need to do is we use our data, and these are all -3, sorry. We use our data to determine X and Y, and then after that we will determine X. So let's determine Y, the order of ClO2. So what we're going to do is we're going to pick, and sorry, these are 1, 2, and 3. So we're going to pick two experiments where F2 is constant. Pick 2 is constant. And so that means we're going to compare the rate of reaction 2 versus the rate of reaction 1. Okay, so what we do is we just take all the data we have. So rate 2 is equal to 4.8 times 10 to the -3. And then rate 1 is 1.2 times 10 to the -3. And then on the other side of the equal sign, we write the rate constant and F2 and so forth. So we write K. The F2 concentration, is 0.1. It's to the X. And then the ClO2 and rate 2 is 0.040, if I write the right one here. That's Y divided by K, 0.1, X, 0.01, Y. Okay, so doing both of these from reactions 1 and 2, doing the rate. Now, you notice a couple things that are going to simplify this right away. The K is the same in both reactions, so they're going to divide away to 1. And you'll notice the concentration of F2 is identical, so this divides away to 1, because X is going to be the same in both cases. The rate law there's only one rate law for all three of these reactions. And so we're left with the ratio of the rates over the ratio of the concentrations raised to the power of Y. So if I do 4.8 divided by 1.2, that's 4. I don't even need a calculator. 0.04 divided by 0.01 is 4 raised to the Y. That's pretty obvious by inspection that the only way we get 4 equals to 4, Y must equal to 1. So we're left with the ClO2 is first order. This reaction is first order in ClO2. That's a better way to put it. All right, so we have Y now. Let's determine X. So which two reactions will we use to determine X? Well, you'll notice that in 1 and 3, the ClO2 concentration is the same, so they're going to divide away. So let's compare rate 3 and rate 1. So rate 3, so this is for X, divided by rate 1 is equal to, now let's put our rates in there, it's 2.4 times 10 to the minus 3 divided by 1.2 times 10 to the minus 3 equals, now I'm not going to put the rate constant in because it's going to divide out in both cases. I'm not going to put the concentrations of ClO2. They will also divide out. So I'm just going to put our concentrations of F2. So 0.2 to the X, excuse me. And then this one is 0.1 to the X also. And if I do this math, 2.4, that's 2. And this is 2 to the X. That means that X is equal to 1. So we have the order of both of the reactions is equal to 1. So our overall order equals 2. All right, now how do we determine the rate constant? Since we have everything, we have all of the other components mathematically of this rate law expression, plug in numbers, and we solve. So we can choose any one of the three. So I'm gonna happen to choose the first one. So let's use reaction 1. So my rate, is 1.2 times 10 to the minus 3. I'm going to use my units at this point. I should have used my units all along, but we'll use the units for sure because it's going to help us with the units of the rate constant. And then the rate constant, and then our F2 is 0.1. I should erase that. Hold on. And then this is molar. And then our ClO2, excuse me, 0.01 molar. And so when we just rearrange this expression, so we're 1.2 times 10 to the minus 3 molar per second divided by 0.1 times 0.01 molar squared, so that's 0.01. That's going to cancel, and we end up with 1.2, and then the units are 1 over molar seconds. And that is our rate constant, determined from reaction 1. We could do the same thing with reaction 2, reaction 3. All of them should have roughly the same rate constant if we do that. And we're left with, these are units for a second order reaction. So we know we've done something correctly. So that's how you take a table of data and convert it into the rate law. So now we know the rate constant and we know the concentration dependence of this reaction rate. So now what do you do in the example? I had a pretty easy example. I had both cases where my X and Y were equal to 1. But it's possible that the order of the reaction is not integral. And so the way you're going to solve for that is you're going to use the natural log. And actually the natural log method is going to work whether it's integral or not. So if you want to be consistent, you can always use this method. But basically if we had rate 1 to rate 2, if we had ratio of rate 1 to rate 2, Our concentrations, I've eliminated the K and the other reactant, raised to the N. And then if we take the natural log of both sides, so we take the natural log of that ratio and the natural log of that ratio, well, it turns out that the natural log of a ratio raised to a power is the power times the natural log of that ratio, which makes it easy to do the math. So if, for example, these are a couple of numbers, if these were the rates from the previous table, if one of them, if the 4.8 was caused by 0.03 instead of 0.04, then we could use this math to determine the rate constant. So this is 1.386, that's n 1.1. Clearly we can see that's not 1, it's actually 1.25, a non-integral order. But that's how you use the natural log to solve for a order that's not necessarily obvious from where it's doubling or quadrupling, so it's obviously 1 or 2 or 3 or so forth. So the key takeaways from this from this video is we'll determine the rate law using initial rates measurements, and this is really kind of a lab practice, empirical practice. You vary those initial concentrations and you just measure the rate. So if you're designing the experiment, actually you get control over those initial concentrations. You can kind of set up your own table, and then once you've determined the order of all the reactants, you can calculate the K, or the rate constant. Should be pretty simple. So until next time.